Hi everybody, Professor Gassimi here. Welcome back to another lecture on AI agents at Michigan State University. Today's lecture is going to be covering three topics: prompt chaining, routing, and reflection. Before we dive into the content for today's lecture, I want to do a quick review of where we are at this point. If you've been following along this semester, you might have noticed we've covered three topics. Our first lecture was on an introduction to AI agents, and what we were trying to do there was give an intuition for why AI agents exist and how they're the natural next step in the historical evolution that comes from the limitations of language models or vision language models alone. We then covered if you want to prompt these language models or vision language models, how can you effectively take advantage of what the scientific literature says so you get the best possible outcomes? So that was our second lecture on prompt engineering. The third lecture we covered was on agentic design patterns. And what we were trying to do there was look at what is happening in the scientific literature, look at common patterns that people do when they're building agents in industry, and try to build an intuition for when you use which pattern to solve which kinds of problems. Now, what these three first lectures have in common is that we were taking a slightly higher view of AI agents. We weren't getting into specific coding examples. We did show you sort of excerpts from papers. In some instances, such as in lecture 3, we showed you kind of how the messages might be passed between the LLM and various stages of its execution and some of the design patterns. But we didn't really get into the next level of detail on the code. What I'd like to do moving forward, so what's on this course's horizon, is a deeper dive into some of those details. And specifically, we're going to be covering a range of topics between now and the end of the semester. And if you want to understand thematically how those topics are going to be organized, you can see those here on the screen. So specifically, the first topic is going to be about how you implement some of the agentic design patterns that we spoke about in the last lecture. If you're new to the class or this is your first time viewing this content, please feel free to visit the channel and take a look at lecture 3 on agent design patterns. We give an overview of some of the common themes there. Okay. The second thing that we're going to be discussing are the mechanisms for the control of AI agents. Specifically, we'd like to review how these agents manage knowledge, they adapt over time, and they interact through some standardized protocols, such as agent-to-agent, model context protocol, and so on. The third thing that we want to cover is content that will provide an oversight and knowledge around integration with AI. Okay, so this is going to include things around when you call a human, how you take sources that come from databases and integrate those into a large language model's response, with the core objective being that we want to strengthen trust in the response. And the fourth specific theme we're going to be covering as we move forward is around scaling and governance considerations for AI agents. I'd like to actually, with respect to this fourth theme, give a call out to some of the people who interact with me on LinkedIn. I had made a post sometime a few weeks back and solicited input from the community who follows me on LinkedIn for input on this class. And scaling and governance considerations was one of the things that was brought up as a theme that people thought would be helpful to cover. Conveniently, these four themes actually do a pretty good lineup against a completely open source and open access textbook that was authored by Antonio Giuli called A Hands-On Guide to Building Intelligent Systems. If you're part of the class, I will put a link in the course materials. If you're not part of the class, you can find this just by popping the name of that book and Antonio's name right into Google. It will come up towards the top of the search results. Great resource, and we'll be using it to sort of scaffold some of the examples that we'll be covering during the remainder of this semester. So with that said, let's dive into the agenda. There's three things I want to cover today, and these three things are thematically around implementing agentic design patterns. So I want to take you one level deeper, help you understand some techniques, and then ground that by giving you some code. so that you know how to do the re-implementation of this in your own personal project. So those three topics we're going to cover are prompt chaining, routing, and reflection. And as we go through today's lecture, I think all three of those will not only become clear in terms of the definition, but ideally how you use them as well. So let's start with prompt chaining, okay? This is simply the process of taking an input that comes from a user, and instead of asking an LLM to solve everything at once, basically writing an enormous prompt with many steps, we take the user's prompt and we sort of decompose it into a sequence of prompts, responses by an agent, followed by a subsequent prompt and a response by an agent, and a subsequent prompt with a response by an agent, effectively decomposing the one large prompt into a series of smaller subproblems that are addressed individually and kind of feeding forward at each of those steps examples from, or rather outputs from the previous steps in order to generate the final response back to the user. What I'm showing you here, just to make this kind of concrete, is an example of a monolithic prompt. And this, as you've seen throughout this semester, is sourced from the reference material that's shown in the bottom right-hand side here. So within this article, there was this wonderful example of sort of what a large monolithic prompt might look like in a common task setting when you're using large language models. So let's read through this one together so that we can contrast the monolithic prompt against prompt chaining, okay? So you're a helpful assistant designed to output JSON, and your task is to summarize the article based on the specific requirement. To complete this task, you should generate the content step by step as follows. So 3 steps are enumerated here for the LLM to follow. The first is to draft your summary for an article based on the specific requirement. The second is to critique your summary, to provide the critical comments and helpful suggestions. And the third is to refine your summary to address all issues in the critique and ensure that the suggestions from the critique are incorporated. So it makes sense, right? Step 1, generate a summary. Step 2, critique. Step 3, address the critiques, okay? What's also included within this large monolithic prompt might be the output format for the JSON object, which naturally might include the summary, the critique, and the refinement, okay? So if we were dealing with a prompt chaining version of this task, as opposed to the giant monolithic task that I showed earlier, where, just for clarity, we would pop the article in here, right? And we would pop the requirement in here. If we wanted to decompose this using prompt chaining, we would take each of the 3 steps that were enumerated in that monolithic prompt, and we try to do them one at a time, passing forward the relevant information or outputs from the first step to the second and from the second to the third. So let's look through one such decomposition that came from the paper referenced here in the bottom right. So we'd start with drafting, right? So let's read this together. You're a helpful assistant designed to output JSON. Your task is to summarize the article based on the specific requirement. The output is JSON format as follows. Summary, which is the generated summary, and then we're going to have an article. We're going to pass in an input article and a requirement followed by an actual requirement. So the way you should read this, just so we're clear, this is sort of like Python syntax, right? If you had a format string, whatever's here in the curly bracket, you would actually input the real article. What's here in the triangular bracket here is just kind of a title or a label to tell the language model in this case that, hey, what follows this tag, is the actual article, which you would replace at the time of doing the inference with the LLM, okay? So what you see is when this step 1 is completed, the output format that was requested is a JSON with summary and the actual generated summary. And so what's going to happen in the second step is we're going to take this summary and we're going to pass it as one of the inputs into the set with the prompt instruction for step 2. So let's, just so that this point is totally clear, let's compare what was passed in during step 1 to what's being passed in step 2. And then, of course, we'll read the prompt here together in step 2 as well. So notice here, after we've defined what we want the output to look like, we say we're going to pass in the article, okay, and we're going to pass in the requirement. Here, we also pass in the article. We also pass in the requirement. But we take the summary that was generated from step 1, the output that comes from this call to an LLM with these instructions, and we pass in the summary into where the curly bracket is here. So you see we're passing it forward. We're following the design pattern that you see here, where we took the first part of the problem, we prompt, we'll have the agent generate an output, we'll have a second prompt here, we'll combine that second prompt with the output from the first step of the agent. That's how we're going to get prompt chaining completed. Okay, so let's read step 2 here. You're a helpful assistant designed to output JSON. Your task is to provide the critical comments and helpful suggestions for the summary, which summarizes the article based on the specific requirement. The output is JSON format as follows. So you can see here, the emphasis is on critical comments. Here, the emphasis was on summarization with the information passed across the 2 steps. Now, naturally, if you understand how this transaction happens between steps 1 and steps 2, going from step 2, which is just moved over here to the left, over to what happens in step 3 is very easy to understand. What's going to happen when you're done with step 2 is you're going to get a critique that follows the instructions in light of the context down here. And then the same way that we did when we transitioned from 1 to 2, we're going to take this output and we're going to concatenate it to the bottom of step 3 to help us with the refining. So for clarity, step 3 might look like you are a helpful assistant designed to output JSON. Your task is to refine the summary based on critique, where the summary summarizes the article based on the specific requirement. You should address all issues in the critique, which is what came from here, and ensure that all suggestions from the critique are incorporated. The output is JSON format as follows. And now we want the refinement, which is the refined summary. We pass in the article, the requirement, the summary that came from step 1, and the critique that came from step 2 to generate the final output from this. So the reason that I'm covering prompt chaining is because the literature, and in particular this paper that provided the examples between the massive prompt and the chaining, report that you get very strong improvements in the performance of your AI agents on complex tasks when you use prompt chaining. The authors of this paper, Sun et al., reported, in fact, that you get a 2x overall preference for summaries generated using prompt chains similar to what I showed you before. So, meaning out of all the records they looked at, the model that did not use prompt chaining was preferred 15% of the time. 46% of the time it was a tie, and around 40% of the time there was a preference for the model that used prompt chaining. So what this tells you is that if you just look at the ratio between 39 and 15, we're doing twice as good or twice as preferred in terms of the quality of the summaries here, and it's probably not going to hurt you even if they do end up being a tie. So great thing for a complex task with multiple steps. Prompt chaining improves it. Now let's get into the practical nuts and bolts of how you do this. And as I go through the code example here, as well as code examples that are going to follow in slides after this, I want to note that I will here, when I call out the code example, I'll be putting down underneath it some of the stuff that goes into the header of the code, so the import statements. And from these import statements, you can see what tools I am covering in order to execute the code example that we're going to be covering. So in this case, you can see I'm using LangChain, which is a common tool to do, very appropriately, prompt chaining. Okay. So specifically, we're going to be looking at LangChain as the ecosystem here. And just like we did in the homework, I'm going to assume you have an environmental file that has access to an OpenAI API key so that we can load your OpenAI API key into the code, and we can use that to make a call to, in this case, ChatGPT's GPT-4 or 3.5 model. Okay, so if this is clear, let's jump now to the actual code. So what do we do? Well, the first thing is, as I mentioned before, we want to load the environmental file, and then we want to make sure we get access to the OpenAI API key that's within your environmental file. This is very similar to what we did for homework 0, so no magic here. The next thing is we're going to choose the LLM that we want to use. This is an OpenAI model, GPT 3.5 Turbo. Okay, so this is pretty straightforward. And then what we're going to do is we're going to write out the prompts that we want to, the prompt templates rather, that we want to define here. So here we've got two, one that's related to summarization and a second that's related to questions. So the summarization prompt is summarize the following text in one sentence. And then you can see it takes an input, which is some text. Okay, this is something we'd want to pass in. And then we have a question prompt, which says, generate one question a student might ask about this summary. And then you can see here, we pass in the summary. Now, where would this summary come from? Well, probably from this, right? And that's why it's chaining, because we're going to have the first step be a summarization, and we're going to have the second step be generating a question a student might ask about the summary. So what LangChain does is it makes some of the orchestration of the prompts from a syntactic perspective easy to do. What I'm showing you down here is functionally how you construct the prompt chain using the LangChain library. For clarity, you do not have to use LangChain. I'm exposing it to you because there are code bases out there that really like it. And I do think that it makes some of the syntax easier. Critically, you can do all of this orchestration on your own. You don't have to use LangChain. Anyway, let's take a look at this. So here's the chain. The first thing we do is we say, well, we want to generate a summary. And we're going to do that by taking this summarize prompt, and we're going to pipe it to the language model. Well, which language model? It's GPT 3.5, the one we declared right up here. Okay. What's going to happen next? Well, once we get this summarization, if we jump here to the next line, we're going to call the question prompt. And then your question to me would be, well, wait a minute, like, what does this question prompt use? Well, it uses the summary that we defined up here. You remember we called it summary here and the input argument? So the summary gets defined up here by calling the summarization prompt. And then down here, the question prompt gets access to the summary, and we pipe that to an LLM for execution. This line, we could have moved it up here if you wanted to make it look similar to what we had. It's just it's a syntactical thing. You can move lines around here and it wouldn't change the outcome. Okay, but the three steps are what? We want to summarize, or rather the two steps are, we want to summarize, and then we want to pass to the question generation prompt. Okay, simple enough. You can run this chain by doing chain.evoke. Chain here refers to what we've defined up here. And when you run with the invoke method, you want to pass in the required JSON object so that we can pull this text input to sort of seed the top of the chain, right? And so we put in here as text, LangChain is a framework for building applications with large language models, and then we can print the results as you show here. When we run that, an actual output of this is, what are some examples of applications that can be built using LangChain's framework? Which I think is a pretty reasonable question that one might ask if we generated a summary of LangChain's capabilities. So it seems like it works, right? Okay, so just a reminder, LangChain, all it does, very simply, we take a big problem, instead of putting it in a massive prompt, we sequence a series of subprompts and we pass forward relevant information from the execution of the first prompt's output to the second prompt's input, and so on and so forth. pretty easy to understand. If you want to see some other code examples using tools beyond LangChain, please feel free to take a look at the hands-on guide to building intelligent systems that I'm referencing down here in the bottom right. So with that, let's jump to routing. So the issue that we had with a prompt chain is that it assumes there is a single pathway, a single series rather of prompts that we always want to follow in order to execute an outcome. But more realistically, what might happen is a user might ask a prompt, and this prompt might be of a couple different varieties, right? So for example, we might have a few workflows, maybe one that's for document summarization, and another that's for looking up things from a database. And the series of prompts that we probably want to ask in that case will be different. So that is to say, we might still have prompt chains, but we might have different prompt chains depending on what we actually want to accomplish. And so what routing does is it puts a language model. It doesn't have to be a language model technically. We could use something else. But it puts usually a language model here, and it asks it, hey, this prompt that the user passed to me, what is it actually trying to do? Is it trying to do the workflow handled by this agent or this chain of agents? There could be a chain here. Or is it trying to do something by this agent or one of the other agents? Okay. And so routing refers to this conditional logic that's placed here at the front. It's like a gate that analyzes the user's query, routes the query to the right agent at the right time based on the inferred intent. Let's go ahead and take a look at an example of this. So this comes from the paper that's referenced down here on the right-hand side, which is a format we've been following all semester. So let's say we have some prompt that comes in here, and let's say each of these are sort of the tokens. These are, the large white cat ran up the hill. Okay, let's say each of the boxes is one of the words there. What the router is represented by is this purple circle here. And what it would do is, as a function of this input, it will choose which of the agent paths to follow. Now, just for clarity, there are some multi-agent treatments that will, when doing the routing, not just choose one of these agents to pass it to. I'm kind of highlighting here that the first one was the recipient of the input, but sometimes they pass it to multiple agents. They get the responses back, and then they have sort of a weighting or an aggregation or some other ensemble method to aggregate the results on this side. Okay, but in a standard routing task, you would take the prompt, you choose which of these pathways to take, you get an output. This output gets passed to the next router along with some concatenation of the input from the original prompt. Okay, so this is looking a lot like the chain, right? You take the original input, you pass it to the next step. You also pass an intermediary output to that step. But the difference here is what makes it routing is that at each of those steps, before we move to the next part of the chain, we're asking an LLM to make some selection for which of these is the most appropriate agent to take responsibility. So we can do this over multiple steps across a chain, and we've now implemented routing. Very straightforward idea. The reason you should care about this is because if you're doing anything where you need to achieve multitask performance, this is going to significantly improve how well your AI agent does. I'm showing you here an example of a mixture of agents, okay, which is actually precisely what's shown here on this slide that I just described. And the authors of the paper that generated that figure tested it on two common evaluation benchmarks for AI agents, Alpaca Eval and MT-Bench, which I encourage you to go and take a look at if you want to understand how these are assessed. And what they basically said, if you look at these gray rows, is that the mixture of agents, so when you do the routing, you get a significantly higher performance compared to GPT-4, which is the baseline. Okay, so you go from 50% up to 65% when you sort of account for the length of the response. So, maybe you want to penalize for the response being too wordy. But if you only care about whether the response is preferred, you can get from 50 all the way to almost 80. That's an insane lift in the quality of the agents that you can get simply by doing this routing effectively. So very impressive stuff. We see similar results, albeit not as impressive here on this other benchmark. Let's look at a code example for routing, just like we did for prompt chaining. Exactly as we did before, I'm putting here the libraries that we're going to be looking at. And you might notice that LangChain is showing up here again. But the other thing I want to point out that's important is we're using, in addition to LangChain, we're using something called LangGraph. And think of LangGraph as what takes care of the gating operations to send you from one place, one language chain, to another language chain, as we're going to see in the example. So here it is. And there's a lot here, but I promise by the time we get to the bottom, it's going to be very intuitive how this combination of LangChain and LangGraph allow us to implement the routing. So let's start at the top. We're going to be implementing a graph. And so what we want to do is we first want to declare what are the things that we want to persist as we pass information between nodes in the graph. Okay? And because we're going to be talking about a graph, I actually think the right place for you to look to understand the code is starting here in the graph space. I'm going to draw it here on the right-hand side. Okay, so here it is. Here's the graph. And what I've done is I've got a router, and this router has an objective. It's supposed to figure out whether a given input from a user is the right response is to tell a joke, or the right response is to do some calculation. And then at the end, we want this to terminate in a response or the end state. Okay, so let's first and foremost look at the LangGraph. So we initiate it by doing a state graph with state, which is what's up here. This is what's going to persist as we move through the graph. Contains the user question. That's going to be needed, right? Because we're going to pass it into the router. And it contains the intent. And this intent can be one of two things, the calc or the joke. Where's this intent going to come from? Well, that's what the router is going to select, right? It's going to figure out what the intent is. And then based on whether it's calc or joke, we're going to choose which of these pathways that we take. And then finally, the output, which is what's going to end up here in the end state, is going to be a string. Okay, we want to be able to return that so we can print it to our user. So what do you notice here? Well, I've got the entry point, set entry point to route. That represents the arrow that you have here. Okay, and then I say I want to add a node, route. And what you notice here is that associated with this node, I have a function that I call that once information enters this node, the route node, this says what you do when you hit the node. And in this case, it's do route. Let's come up here and take a look at what do route does. It takes the state, that's the stuff up here, and what is it interested in? Well, it wants to take the this intent that's within the state that maps to this intent, right? That we want to compute. And the way it's going to do this is by taking the route chain, so that's the prompt chain, and invoking it with S. Okay, what is S in this case? S is the user question. Okay, so how does this mechanically get passed forward? Well, notice we took the state, which is of this type. The state contains a user question. When we called or invoked route chain, which is a prompt chain that you see up here, let's read it together. We say route as calc or joke, only one word, and take the user question. Well, the user question is pulled from here in the state. So we pass in the state, that comes through to this route chain, and then this user question gets pulled from the state. Okay, just as you saw in the LangChain example previously, the syntax for how you execute LangChain is you pipe this to an LLM, and in this case you pipe it to as well a string output parser so that it makes things a little easier to read. Okay, great. So let's come back to our graph. We understood how we set this entry point for route. We understand how to add a node. Okay, so that's what's responsible for creating this. We also understand what function it does, doRoute, which effectively takes the user question and tries to figure out, is this calc or is this joke? And it's only going to respond with that one answer. Now, what we want to do next is create a conditional edge between the route node, okay, and the other nodes here, right? We want to basically go to joke, and we probably are going to have a different prompt chain for joke than we are from calc, right? There's a different way we have to prompt here. And so what this conditional edge does is says, we want to go from route, and then as a function of what's in the intent, which is what gets filled in when we call doRoute, right? As a function of this, what's in the intent, we want to either go to the calc node, or we want to go to the joke node. So specifically, if the intent is calc, go to the calc node. If the intent is joke, go to the joke node. Okay, pretty straightforward. It's basically operationalizing this decision that you see here. Okay, well now we need to, for the joke and for the calc nodes here, we have to similarly define, instantiate them and what they do, just like we did for route. So let's come here first to the calc node. You can see this calls the doCalc function. The doCalc function takes the same state. And what it's going to do is operate on out. It's going to update this. It's going to do that by invoking the calc chain and passing in the user question. So let's come up here to the calc chain. And what you see here is this sort of makes sense, right? Where the router has sent a question that it believes requires a calculation. And so therefore, the calc chain says, compute step by step, give the final number only, and then it passes in the user's question, which gets executed by the LLM and cleaned up a little. That cleaned up output is what gets stored in out here within the state. Okay, that's what this node does, calc node. And then finally, you can see the joke node is structured very similarly. In fact, the doCalc and the doJoke are almost identical. The only real difference is the prompt chain that's used. Whereas the calc chain said, let's compute step by step, final number only, the joke chain says, respond with a short joke about, and then it puts the user question. Okay. Notice here that we can add an edge that goes from the calc node to end, and we can similarly add an edge, this time not conditional, that goes from the joke node to end. We add this compile, and we now have the LangGraph, which says, how do I conditionally move from the output of the router, based on the output of the router, to these different chains? And you can see here that we did it for one router, but we could have many routers. We could have 2-3 layers of routing that are conditionally composed so that we could have many different subpaths where we execute different language chains before terminating in the end state. Okay? Great. So if you understand this graph, I think, and how these functions support the implementation of the graph, you've really got this. I'm showing you down here an actual example of me running the app here with a user question of what is 17 times 23, and it outputs 391, and me asking it, tell me about penguins, and it outputs, why do penguins like talking to strangers at parties? Because they find it hard to break the ice. I actually think this one's pretty good, to be honest. What did it do in these two demos? Well, it just followed the graph that we set up here. It went to route and it asked, is this a calc or a joke? Use one word only. And in the case of this first example, what is 17 times 23? It chose calc. It then routed to the calc node, and it did the chain, the LangChain associated with calc. In this place, computing step by step based on the user's question to obtain a final number. Okay, so pretty straightforward. This is how you set up a Lang graph, and you orchestrate it with LangChains. So now let's talk about the third and final item on today's agenda, which is reflection. So reflection is the idea of an agent being critical of itself in order to improve its response. Okay, this is sort of like when you're going to write an essay or writing software. If you're writing that software alone especially, there's a process where you kind of look at your code, you observe deficiencies, and then as a function of those deficiencies, you make updates to your output. And the notion of reflection in AI agent development is very similar to that. You basically have a user and they specify a prompt. This prompt is sent to a producer. So it generates the response as a function of what the user input here. But then before the producer responds back to the user, i.e. before it generates this output, it passes along to an agent, another agent, who performs a critique. Now, this is going to remind you, if you were paying attention, to the prompt chaining example that I showed you earlier, right? Where we have the 3 steps. And you may recall that the second step in the process was to actually perform a critique of the summary generated in the first one, right? So common pattern. Producer produces, a critique happens of the input. This gets sent back to the producer who takes the critique, makes an update, and sends it back to the user. What I'm showing you here is an example from another paper. The link to the paper is down here on the right, where they're showing you a concept that they refer to as reflection, where for a given task, in this case, it's a decision-making task from a pretty cool text-based game, which I'll talk about on the next slide. They ask the agent that's operating inside the game to make some decisions. So for example, the task might be clean some pan and put it on the countertop. The agent then, the actor, as they call it, proposes a trajectory. Well, hey, if I want to clean some pan and put it on the countertop, I need to take the pan from the stove burner and observe what happens, in this case, nothing. And then I'm going to take another action, which is try to clean pan with the sink basin. But nothing's going to happen because it failed on this first action, right? It then does an evaluation. It basically looks at these action and observation pairs and says, oh, nothing happened. And it does a reflection on why things might have gone wrong. I tried to pick up a pan in stove burner 1. The pan was not on stove burner 1. And so then it amends this by, in the next trajectory, trying to take pan from the second stove burner and putting it on the countertop. Okay? So this process typically continues in a loop until you converge to whatever accomplishes the original task here. So think of this as occurring within a for loop. I'll leave it up to you to review these other 2 examples here. They cover the same idea. If you've got it for decision making, I don't think I need to cover the other 2. The reason people do reflection is because when you have to accomplish a sequential task, what they found is that you get significant improvements in decision-making capabilities within benchmarks. Specifically, the graph that you're seeing here, which was sourced from the paper down here, referenced in the bottom right, looked at the ability of an agent, it was GPT-4, when it's using just simple old React, which we covered in the previous lectures, versus when you added this reflection dynamic to GPT-4. So instead of just reasoning and acting once up front, it did reasoning acting, and it added this reflective component over a series of trials, steps that it made in the game. What is the game? Well, AlfWorld is this kind of natural language game where an agent exists in a world. The world is described in text, and a task is described, and it sort of has to choose from a set of options to navigate this world and accomplish its tasks. What the graph here on the left-hand side shows you is that by adding the reflection, you get significant not only gains in the performance across trial steps, so the steps you need to accomplish the task, but that those gains continue to grow across trials. They don't flatten out like when you're using just a React only here. Okay, so reflection really helps improve decision-making capabilities and benchmarks, particularly when the previous set of decisions impacts the next ones moving forward. So let's look at another code example here, so it's clear how you implement this in practice. Here again, we're using LangChain, and because there's no kind of routing that's strictly required here, we're going to be just using LangChain. There will be no LangGraph. It's just a LangChain implementation. Let's dive into the code. Some of this should look familiar. This is just like the previous two examples. We instantiate our LLM. We're going to use GPT-4o Mini in this case. And we also instantiate a parser that's going to just clean up some of the output. And what we want to do is, let's say, 3 steps. We want to draft a document. Okay, we want to critique the document. And then we want to do a revision to the draft based on the critique. And what we'd like to do is probably, given that this is reflection, we'd like to do that in a for loop until we converge to an answer. Okay, so let's first go through these 3 chains, these 3 prompt chains. Once we understand the prompt chains, we're going to cover how the reflection is functionally executed down here. Okay, so the first one, when we're drafting, we're going to ask to write a concise answer to the task. We're going to pass the task in. We're going to ask it to limit to 3 sentences. That will be piped to an LLM and cleaned up. When we're critiquing, we're going to say, you're a strict reviewer, critique the draft for correctness, clarity, and completeness. We pass in the task. We pass in the draft. We ask it to list concrete issues and improvements, and that if there's none, to reply, hey, there's no issues. This, by the way, the end here, if there's nothing, reply with no issues. This is going to be important because if we're going to do this in a loop and keep revising, we need an exit criteria, right? We need it to tell us when it thinks we've fixed this enough to a point that we can let it through, okay? There's more sophisticated ways to do this than, just asking it to respond with no issues. You can define a score or another method, and then if it's above a certain threshold, it could pass. Okay, the third step, revision, here might be revise the draft using the critique, produce a final answer, 3 sentences max, and then here we want to pass the task, the draft, and the critique, and then we're asking it to produce the final. Now, what do you notice here? Just like you noticed in the prompt chaining example earlier. Here, when we're drafting, notice I didn't pass anything in other than the task. Here, when I do the critique, notice I passed the task as well as the draft. Where did the draft come from? Hey, it came from up here. Notice that when I'm doing the revision, I pass in both the draft that came from up here, I pass in the task, which is what the user gives, and then I pass in the critique, which comes from step 2. So this chaining, you should see this pattern, right? As you're building things, you take what came from the previous step, you pass it forward. All right, so if you understand these 3 chains, now let's talk about how we orchestrate these into the reflection pattern. So what I have here is a function, reflect. It takes a task, that's what the user gives. And then in this case, I put a max number of iterations because, We may want to stop it from reflecting an infinite number of times, right? Ideally, it would do this in hopefully twice, maybe after 2 cycles of reflection, it's done. But in case we get caught in a funny loop, we probably want to set the maximum number of iterations to kind of kill it after that. Okay, so in this case, I've set it to 3. Here, I'm going to create a draft, which is by invoking the draft chain. That's right up here. That's going to take whatever I pass in as the task. This task will work its way up, get injected here, and I'm going to execute this with my LLM, which in this case is GPT-4o Mini, and I have a draft now. Now what I'm going to do, given the draft, is I'm going to start my for loop. And basically, we're going to go from the starting point all the way up to the max number of iterations, which is 3. And we're going to start critiquing by calling the critique chain. We're going to pass in, remember what this required? It required the task and the draft. So we're going to pass in, when we're invoking, task and the draft. This is just to do some string cleaning at the end. We have our critique. Now remember, the critique chain said, if there is a response that has no issues, respond with no issues. So the natural thing to do here is to say, well, if this thing responded with no issues, then we're done. We don't need to keep iterating, just return the draft, we're done. But if it did not respond with no issues, then we want to call the revise chain down here, which will take the task, the draft, and the critique, and it's going to generate the next step, the revised draft. We'll continue iterating through this, obviously, until we either hit the maximum number of iterations or we converge. So let's look at the execution of this example where we reflect on explaining transformers to a high school student. This is the actual draft that the LLM GPT-4o produced on its first iteration. It said, transformers are a type of neural network architecture designed to help computers understand and generate text, like sentences and stories. They use a mechanism called self-attention to identify the most important words in a sentence, allowing the model to focus on context, such as determining that in, quote, the cat sat on the mat, cat and mat are key. Widely used in applications like language translation, e.g. Google Translate, and chatbots, e.g. ChatGPT, transformers also power technologies for image processing and summarizing texts, showcasing their versatility in modern technology. Now, I don't know about you. I mean, I think most high school students are super clever, but this might be a little bit over their heads, right? I mean, some of the examples here, for instance, talking about mentioning a neural network architecture. They may not understand what's meant by architecture in this context. Self-attention, okay, might also sort of confuse them. At least that was my take on it when I reviewed this draft. And it turns out that when the critic inside of our reflection system had access to this draft, it followed our instructions and looked at the 3 criteria that we specified. So for correctness, the critic said that the explanation correctly identifies that transformers are used in machine learning, highlights the importance of self-attention, but it could be more precise about how self-attention works. For clarity, it said the language used is somewhat technical, may not be easy to understand by a high school student. That was exactly my concern as well. Said to consider simplifying the terms, providing definitions for self-attention, and weighing the importance to enhance understanding. And finally, for completion, it gives a similar level of depth of critical feedback. Now recall, the way we wrote our code is we take this draft, we take the critic, it gets passed to the next step, which tries to generate the second draft. And in this case, this is actually the draft that ends up coming out the other side. I'll read it aloud, and I think you'll probably agree it actually did a pretty good job addressing the concerns and making this easier for a high schooler. So let's read it together. Transformers are advanced neural networks used in various language tasks, such as translation, summarization, and question answering. They work by analyzing all words in a sentence at once, similar to how a group of friends might collaborate on a project, ensuring they stay connected while working on their individual parts. By utilizing a mechanism called, quote, attention, transformers effectively understand the relationship between words to generate accurate and meaningful outputs. Much more accessible for a high school audience. So friends, that's it. This covers our lecture today on prompt chaining, routing, and reflection. Hope this was clear. Hope the code examples are helpful. I will see you in the next video.